Hello everyone, welcome back to another Leetcode video. Today we're going to be doing problem number 48, rotate image. The problem statement is the following. You are given an n by n 2D matrix representing an image. Rotate that image by 90 degrees, clockwise. The catch here is that you have to rotate the image in place, which means you can't return a whole new matrix, you have to modify the original 2D matrix directly. So the solution here actually hinges on the fact that you can't do that 90-degree rotation directly. You have to do a sequence of other operations first. Namely, you have to first reverse all the numbers within a column and then take the transpose of that matrix. Let me show you exactly what that looks like. So I've reproduced example 1's matrix right here. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're going to apply two operations, just like I said before. The first is reversing all the numbers within a column, and the second is taking the transpose of that resulting matrix. It turns out that this matrix, after all those operations are applied, is the same as just rotating rotating the original matrix by 90 degrees clockwise. So the problem now becomes, how do we reverse all the numbers within a column, and how do we take the transpose of a matrix? Let me show you the first operation first. So let's just look at the original matrix here. We know that this 7 has to come up here, and this 1 has to come down here. 4 doesn't change. So what we can do is initialize a pointer at 7 and a pointer at 1, and then just swap them. And then we're going to move to the next column. The pointer is now at 8, and the top pointer is now at 2. We'll swap them. And then we'll move both pointers to the right once more, and we'll swap them. Eventually, you're going to get a matrix like this. And this was quite an easy example, but for more advanced matrices, all you would have to do is initialize one pointer at the top, another pointer at the bottom, swap the numbers, and then if that column is more than just 3 numbers, you're going to have to move the bottom pointer up by 1 and the top pointer down by 1. We can do a quick example just to show you what that looks like. So if we have 1, 2, 3, and 4, then we would initialize a pointer at 4, initialize a pointer at 1, we'll swap 1 and 4, then we'll move the bottom pointer up and the top pointer down, and then we'll swap them. So eventually it should look like this. 4, 3, 2, 1. So you can actually use this algorithm for reversing a string or reversing a sequence normally. You don't have to use it just for matrices. Okay, one more thing to note here is that after this step, where there's a pointer at 3 and a pointer at 2, if you move the bottom pointer up by 1 and the top pointer down by 1, they're actually going to cross each other. And once they cross each other, that's when we know the algorithm should end, because there are no more pairs of numbers to switch. Okay, so that's the algorithm for the first part, which is reversing all the numbers within each column. And then we have to take the transpose of the resulting matrix. So the transpose is no more than just taking each column and making it a row. So the 741 column becomes a 741 row. 852 column becomes this 852 row. Of course, you can also take the 789 row and make it a 789 column, and so on and so forth for all the other rows. Now, to take the transpose of a matrix is a little trickier than you might think. The first key to understanding how to take the transpose of a matrix is understanding what numbers change and understanding what numbers don't change. So numbers that don't change lie on the diagonal. 753 is here, and 753 is there. They don't change at all. The numbers that aren't on the diagonal do change, though. So it turns out that the transpose is actually reflecting all the numbers across the diagonal. This 4 comes up here, and this 8 goes down there, for example. Now, given that information, we can write the following algorithm. First, we're going to iterate through all the diagonals. So 7, 5, and 3, we're going to iterate through all of them. Let's say we start at 7. If we start at 7, we're going to have to look at all the numbers on the same row as 7, as well as all the numbers on the same column. So let's say we look at 8 first, and we look at 4. Now, since we're reflecting numbers across the diagonal, we want to swap 8 and 4. And then, once we're done with that, we're going to move on to the next number in the same row as 7, and the next number in the same column as 7, which is 1 and 9. And again, since we're reflecting across the diagonal, we're going to swap these two numbers. And in the end, you're going to get 741 as the row, which is correct, and 789 as the column, which is correct. Now, that's only for the first diagonal. Once we move on to the second diagonal, which is 5, we're going to do the same thing. We're going to look at all the numbers in the same row and in the same column as 5. But we're only going to look to the right when it comes to the row comparisons, and we're only going to look down when it comes to the column comparisons. So if we follow what we just said, we're going to compare 6 and 2. And then we're going to see that we actually have to swap these two numbers. So 6 comes down here and 2 goes up there. Now notice that there's no number after 6 for me to visit. So I'm actually done with processing 5. Now let's move on to the last diagonal, which is 3. We're going to look at all the numbers in the same row and in the same column as 3. But there's nothing to the right of 3 or nothing below 3. So we can just finish processing 3 right here. In the end, we actually get a matrix like the following: 741, 852, 963. That's exactly what we want. So our algorithm, again, is just reversing all the numbers within each column and taking the transpose. Let's see what the code looks like. So let's say that we have a variable representing basically the number of rows or columns. That's just n. So n equals the length of the matrix. And then let's say we implement the first operation, which is basically reversing all the columns within the matrix. Reversing all the numbers within each column of the matrix. So luckily we have our example number 1 right here, and we can use it for reference. So first, we actually have to iterate through all the columns of the matrix. So for this, we can just say something like for k in range n, right? Because it's an n by n matrix. Okay, now let's say we're within one column. How do we reverse all the numbers within that column? Well, we're going to initialize 2 pointers. We're going to call them I and j. I equals 0 and j equals n minus 1. So that means I is going to start here at 1 and j is going to start here at 7. And then we're going to say while j is greater than I, we're going to do some logic. Basically, we're going to say matrix of I, k, matrix of j, k is equal to matrix of jk, comma, matrix ik. So what does this line do? Well, I'm basically saying that I'm looking at numbers within the same column here, because all of them have k in the column index, right? But I'm going to be comparing 1, which is where I is right now, to 7, which is where j is right now. And basically I'm going to say, let's swap them, right? Because we want to reverse all the numbers within this column. So that's basically what this line does. And then we're going to have to update our indices, our I and j. That bottom pointer is going to have to move up by 1, and that top pointer is going to have to move down by 1. And then, when these two pointers cross, we're going to terminate this while loop and finish reversing all the numbers in each column, or all the numbers for that column. Okay, so that's the first step. The next step is taking that matrix and doing the transpose. Now, in order to do the transpose, remember, we said we have to iterate through all the numbers in the diagonal. So let's just use another letter for L in range n. N is 3 here, so there are 3 diagonals, which makes sense. And then we're going to say for m in range 1 to n minus L. And then we're going to do something like the following. We're going to say matrix L plus m, comma, matrix L plus m, L equals matrix L plus m, L, matrix L plus m. So let me explain what this line does. Basically, we're going to be looking at all the diagonals. Let's say, for example, we're looking at this first diagonal 7, and we're going to offset from that spot from within the same row or from within the same column. So L plus m might bring us to 4 in the same row, or L plus m might bring us to 8 in the same column. And then once we get to these positions, we're going to swap these two numbers. Again, this is just implementing the same algorithm I described before, where we're basically visiting all the numbers to the right and to the bottom of our diagonal and swapping them. Okay, so that's what this for loop does, this double for loop. Now, we should have a matrix that looks exactly like we want it to. Let's see if it works. All right, so we have faster than 85% of Python 3 online submissions. So let's go over the time complexity really quickly. Well, let's actually just go through each line. So this is constant time, right? But this is basically 2 loops. The first loop runs for big O of n time, and the second loop is also linear in time, because you're basically having 2 pointers go and explore the entire sequence and reversing each number in this sequence until they reach the middle. So that's going to take linear time, right? Since you're basically traversing the entire column in that matrix. So linear time, so overall this whole operation is quadratic time. Now this for loop is also linear, and this for loop is also linear, right? And we can see that that's true simply by seeing that we start at 1 and we end at n minus L. And in the worst case, this might mean we have to basically do big O of n operations. So this whole double for loop is quadratic time. So quadratic time for this double for loop, quadratic time for this double for loop. The entire algorithm is quadratic time, n squared. All right, I hope that explanation helped you. If you like this video, please comment, like, and subscribe.